Okay, thank you everyone for participating in this special event. Here we would like to introduce how we use the OpenAI's Whisper to do a practical application for the AI in live streaming. Okay, next slide. Yeah. Okay. Yeah. Okay, first of all, I have a short introduction about ourselves. So I'm Alex Liu. I'm the co-founder and the CEO of NETINT, oversee the product management and the sales marketing part. Sean?
Yeah, and I'm Sean Varley. I'm Chief Evangelist of Ampere Computing. We do server processors for the general purpose processors for the ARM ecosystem.
Okay, so a short introduction about NETINT as well. So my partner and I started NETINT in late of 2015. So our mission is to build the next generation of the video processing unit. So after a few years of growth, right now we have about 200 senior engineers already. And we have achieved tremendous achievements by winning a lot of the key customers, the hyperscalers, and also well recognized by the market. And we are very proud to say that we won the 2024 Tech Emmy Awards. So it's really amazing for us as a small team. Okay, next slide. Okay, so first of thing, what is the video processing unit? It's a customized built ASIC that has only one purpose, to process the video. And one of the advantages by processing video, not using the general purpose CPU, but through the dedicated ASIC that can bring tremendous of the density and the performance improvement. Here is a number that you can see that this is not a theoretical number that from some academic paper, but is from a real customer of us. So before they start using the general purpose CPU to do all the video transcoding and their whole infrastructure and also the total cost that is about 10 million. And later on, they have to change, right? Because this is a big impact of business. So they switch to the GPU and the cost are down to 3.4 million. And when they found us, they switched to the ASIC solution. Now their cost is only 1.4 million. So we saved 86% of the total cost. And this is just one of the typical customer. There are more and more customers have the similar fundings, even greater fundings. Okay, next slide. So I love, there's a quote very well that's provided by David Ronca, who is the head of the video encoding expert at Meta. So he said there are two types of customers in the video business. Those are using video processing ASIC, and those that will. I really love this quote. And we found this during this few years of the journey in the market, we found that it happens everywhere, no matter it's the big customer or small customer. It happens every day. Here on the right side of the slides, you can see there's also another number that I can show you. That's a typical number that if you run 10,000 HD streams, and what is the cost or how many servers you need to run that, you're providing relevant necessary ladders to the customer. And you can see if using the general purpose CPU, you will use more than 1,000 servers. While using the ASIC, dedicated ASIC, you only need 32 servers. And that is exactly the reason why Google built a customized ASIC and for the YouTube. And so does the Meta, right? But those titans build those ASICs only for themselves. And we build this ASIC for the industry. So it's open to everyone to use. And because we serve so many customers, we familiar all the workflows, all the know-hows accumulated in those years. So we can say that our product can provide the industry the best of the compatibility and also easier to use. It's very flexible, and also we're catching up all the latest tech of the release. For example, the latest FMPEG-1, we support that. Anything new that needed by the customer, we support that very quickly. Okay, next slide. Here is the typical 1RU server that we provided to the customers, which include 10 of the T1U video processing unit and also state-of-the-art software stack. It also shows the typical of the hardware blocks that in our VPU. It has a dedicated of the codec engines and also audio codec engines and also AI module that can run the CNN modules very efficiently, like doing the normally like the classification, object detection, and also use those kind of AI inputs to fine-tune the encoding process to improve the video quality. It's doing very well. And the best thing is it built into the video pipeline. It didn't increase any latency. So you get the throughput together with the high throughput of the video transcoding pipeline. So in this typical setup with 10 of the T1U units, we can support 320 full HD transcoding in parallel, no matter it's H.264, H.265, or AV1. And also it has a built-in 2D engine. It can do very fast of the scaling or the watermarking or the other pixel level manipulations. So that's also the video engineers needed every day. On the software side, we have fully support the FMPEG, GStreamer, GPEG, Unified Origin, those kind of very popular framework. And we also support the low-level APIs that support to the engineers. If you have advanced requirements, you can call the API directly. Normally, the hyperscalers or advanced engineer will use that way. It's very flexible and very efficient. And also that all products built into based on the PCIe MME protocol. So basically, we can adapt to all the operation systems, all the kernel versions, all the frameworks like virtualization, Kubernetes, right, Docker, with no effort. By nature, it support that. So what customer typically they need is to apply a FM patch to your current workflow. That's it, done. So all your workflow keep as it is. So, okay, next slide. Of course, in this server, we have also a powerful partner, the product inside. There's a 96-core Ampere CPU there. It's very high efficient, very high performance, highly applicable, scalable, and also power efficient. Of course, Sean will talk more later. Okay, next slide. And people always say, oh, what the 96 core can do for you? The best thing is, because of all the heavy lifting video work done by our VPU, so the 96 core is there for your other advanced usage. Is there for you, right? So what they can do? So it can do everything. But for the video-related task, it's very commonly to see that we can decode the legacy MPEG-2, right, very efficiently. Doesn't use too much of the CPU. We also can decode the latest AV1 with high stream count as well. And for the legacy applications like deinterlacing, it can handle very well, especially compared to other x86 CPUs. I can see that the Ampere CPU doing the job is the best. That's why we select Ampere after we do all the benchmarkings for a few months. Yeah. Okay, next slide. So we have talked enough about the hardware side. Of course, on the software side, we have a lot of innovations as well. So NETINT start serving the hyperscalers at the start. That's why we are very focused on the low-level applications and also FMPEG support. So all our customers using very frequently to use FMPEG, even the lower layer API calling. But after we serving more and more customers, we realize there are so many professionals. They are also focused on the business innovation or the architecture innovations, but they are not want to spend too much time on the FMPEG code lines. That's why we built the Bitstream Edge, which is a simplified GUI application that can configure and distribute the live streams without touching the FFmpeg command line. So it's code-free. And also we have the pre-configured the templates that help you to manage and monitor all the workflows through our web API or through the integrated API. So this is a very efficient tool for the professionals. They want to focus more on their daily work instead of the low-level coding. Okay, next slide. Of course, the biggest thing we want to talk about today is about the OpenAI's Whisper. We built that into our live streaming server, of course, the Ampere edition. And also, I would say that OpenAI's Whisper is a game changer for the industry. It removes the language barrier for the non-native speakers, and also it improved the accuracy or the comprehension of the contents and let the application to engage wider users. It's a game changer for the industry. And the most beautiful thing that I would like to talk about that is this is not kind of the academic research or the futuristic talking. This is how practically that we can bring this new technology to the professionals. So in the typical server configuration we presented before, that can handle 320 of HD streams transcoding, and also it can run of the Whisper 40 sessions in parallel. So if you consider the lidars you will put into your streaming service, it's a perfect match. And by bring that kind of the high performance built into the same server, that gave you the tool that you needed every day, that you can bring this service to your current infrastructure immediately. That's why we are so excited about this and try to tell more and show more. Yeah. Okay, maybe. Yeah. Okay. Yeah. This is the demo we want to show today. So basically, we build a true live FFmpeg session, live service, bring into this room. So we build OBS that can capture the video and audio from here, and also through the demuxer to separate the video tracks, that all the video will go through our VPU to do like the decoding, overlay, scale, encoding, and generate the video ladder, send out, right, as normal. And for the audio tracks, we will decode, resampling, and go through the Whisper AI API running on the CPU, and also encode and generate the subtitle tracks and build into the packager and stream out. This is a live FFmpeg generated HLS, and you can see how it works later. Okay, next slide. This is the Whisper's function block. I think that's too much detail. We can skip now. Yeah. Next slide, please. Okay, we already talked about this, so that's okay. I think we can jump into the demo session. Sean, do you want to run some tests for us? Yeah.
All right. I think Kenneth's going to bring up another microphone so we can show you this this Whisper appliance in action. We have to change microphones, so bear with us here. Okay. I'm going to have to go. All right.
I can hold it for you.
Thank you.
Yeah.
Okay, so I think we'll switch screens, if I'm not mistaken.
Yes.
Yeah, okay.
We're
going to switch screens, and then maybe what I'll do is I'm going to sit down here on the stage.
Nice.
This one. So, yeah, there we go. So now you're starting to see the actual Whisper. I can't, not for this demo, but I'll switch back. Yeah.
That's fine.
Sorry. All right, so what we're seeing right now is the actual Whisper running through the we're seeing the actual audio. I'm getting feedback as well, so that's going to be a little confusing. But hopefully you are seeing the actual.
It's working very well.
going through the actual demo box. And we're seeing
It's coming through the TV, right?
yeah, it is. It's coming through the TV.
So just a remote on the TV or kill the TV.
It's okay. So one of the things that that's interesting here is that you'll see that there's a delay, right? That's a delay going through the setup and the actual framing of the video stream, and then the separation of the audio track to be run through the Whisper model. And that's going to actually go, of course, on any implementation of this technology. So that's kind of what you're seeing here now live. Thanks to Kenneth for actually getting this working and the crew in the back. As you can see, it's a lot of extra implementation here to get this all running. But I'm going to leave the actual transcription demo now, and we'll go look at a little bit more of the actual box and kind of what's in the box from an Ampere technology perspective. Okay, we'll switch back to the main slides. Thank you.
Okay.
Next slide, please. Okay, next slide. All right, so Ampere is a company that builds very high performance and power efficient server processors. And essentially, when we put this company together, we were about 6 years old. We knew that we were living on borrowed time as a society, as an infrastructural provider, community, industry that is building data centers. And the reason why is because for many, many decades, it didn't really matter how much power you burned in a server because there was plenty of it. But the fact of the matter is the demand has now overstripped our ability to produce inexpensive power. And so the time is now to change that whole paradigm. The paradigm needs to change because we are starting to run out of data center space. We're starting to run out of inexpensive electricity. And we're starting to see actually more and more governance put on data centers worldwide as data centers continue. All right. All right, this is better? Okay. So we're starting to see that the time is really now to shift this whole paradigm, because computing is getting more and more powerful, but it's also getting more and more expensive to run from an electricity perspective. Next slide, please. So Ampere has a different philosophy. We are a different beast, if you will. We actually, for decades, like I said, the x86 ecosystem was riding on Dennard scaling, which is on the left-hand side of the slide, which is the steep part of that curve. It's how you get performance through frequency scaling. But about 7, 8 years ago, this started to level off. And Ampere has started to take the only remaining path for adding performance, which is to scale out in core count. And scaling out in core count is a very different philosophy. Of course, x86 does it too. They have multi-core processors as well. But Ampere is taking it to a different scale. Essentially, we are not doing turbo frequency. We're not doing hyper-threading. We're not doing scale-up accelerators. We're giving people many, many high-performance, high-efficiency cores. And the difference is what you see on the right-hand slide. Now, what you're seeing here is spec-int rate, which is a measure of integer performance in server processors. And what you'll see here is that Ampere can actually do twice the performance at about half the power of typical x86 competition. That means we are very, very efficient. We can actually deliver a ton of performance. In this case, what you saw earlier with Whisper is we're doing AI in parallel to all the video streaming that our friends at NETINT are doing in ASICs for doing the actual video transcoding. So we're delivering a video distribution box that is very, very high power in terms of what it can actually do, but also very, very efficient in how much electricity it draws. Next slide, please. So to illustrate this, I'm going to kind of look at a model of a web service that is video heavy. Okay, so we asked the question, if you had a typical web service running on an infrastructure, whether it was on-prem or in the cloud, and you asked of it about 1.3 million requests per second, as measured by something that's going through a web interface, how many racks are required to actually service that in a video-heavy workload? Next slide. And here is the setup of that actually video-rich web service. Something on the front end to actually handle HTTPS requests. Nginx is a very typical application in this realm. Redis is a key value store, something to retrieve objects. And then you have something that's doing about 20% of the workload, in this case, doing video transcoding, and then a back end, because you've got to store all that video through a database like MySQL or Postgres or something else like that, right? So these are the components. Here you're seeing a measure of efficiency. Performance per watt, which is a very good measure of efficiency at a socket level, so a server level. And you're seeing here about almost 5x the efficiency using the Ampere processor versus the Intel and AMD processors, which are in the grayscale there. And then look at Redis, about 4.3x better in efficiency. H264, about 2.5x better efficiency, and then down at MySQL, about 2x the efficiency. You might see that there's a very big spread here between performance of different kinds of applications. Why? Because different applications have different limitations. In the case of MySQL, it's very I/O bound. So the compute doesn't necessarily give you quite as much efficiency because you're waiting on disk, right? You're waiting on drive to actually do a lot of things. So, but by and large, what you're going to see here is somewhere on the order of 3 to 4x efficiency gains by using an Ampere-based cloud-native processor. Next slide, please. Now, here's the kind of punchline for all of this. To answer the question I asked earlier, how many racks or how many servers does it take to service that 1.3 million requests per second, you can answer it in these 3 ways. The first part of this is look at how many CPUs are required to actually service that infrastructure. Ampere's case, 35 CPUs. That's a single processor. In the AMD case, 49 CPUs, or if you're using dual socket servers, it's going to be almost 25 servers to be able to actually service that. In the case of Intel, 40 servers. Now look at the power consumed in the middle. In this case, that 1.3 million requests per second is going to take about 12.7 kilowatts. That's realistically about how much power you can actually put into a rack for a typical rack. Of course, hyperscalers do more, and there might be racks that do less, especially at the edge. But we chose this particular workload because we wanted to fit it in one rack, 12.7 kilowatts power constrained. Look at the AMD case, 22.7 kilowatts, and the Intel case, almost 35 kilowatts. What does that mean? They have to spill into other racks because they're power constrained. You may be seeing this in your own infrastructures where you're not able to fill racks out because x86 servers have gotten so power hungry, they're consuming the entire power budget of a rack. So the end of this then is we fit in one rack, the AMD servers in 2 racks, and the Intel in 3 racks. That's the kind of choice we're giving you, and what we're doing with our friends at NETINT actually extends this, because if you're doing a lot of transcode heavy workloads, you're going to use these ASIC-based accelerators to not only increase the performance magnificently, you're going to also drop the power of the actual infrastructure to be able to do that computational processing. Next slide, please. Okay, so we talked about Whisper. Now, what's running in the demo that you just saw a moment ago is Ampere AI technology. This is GPU-free AI technology. What we do is we have a lot of cores. There's actually, in our Ultras processors, up to 128 cores. Alex said earlier there was 96 running in this particular demo, but we actually can run up to 128 in the Ultra line and up to 192 in the Ampere 1 line. That's a lot of cores. We actually have 2 vector units, which are the units that do computational math in each core. So that's twice the actual resources than the number of cores. In this case, 128 cores would give you 256 vector units. That's a lot of vector units to actually spread a load out across. So what we've done is we've actually put in these open frameworks that are optimized for our architecture. We acquired a company about 3 years ago that does acceleration and optimization in this realm. So now what we're delivering is open source frameworks, PyTorch, TensorFlow, Onyx, others are supported, and they're doing the model optimization, the graph mapping to the actual hardware interfaces down below, and giving you a very accelerated profile for doing models like Whisper. But it's not just limited to Whisper, right? If there are other language models that you are interested in using to do transcription, this is a general purpose processor. Any of these models will run on these frameworks. No change required. So that's the kind of technology you just saw in this demo. It's one of the reasons why we can get to the densities that Alex mentioned. He said, 40 concurrent streams transcribed. That's the power of this optimized technology. Next slide, please. So here's a couple of benchmarks across other models, right? What you're seeing here is DLRM, which is a recommender engine. This is the typical engine that does like similarity searches, things that recommend you videos through a video on demand service, or give you suggestions on the place you might want to eat because you're interested in Vietnamese or something. So that's DLRM. BERT, of course, is one of the foundational transformer models for large language processing. Whisper, we just saw, a very highly optimized transcription and ASR model. And ResNet's a vision model. So these are the kind of benchmarks you're seeing here against not just other CPUs like the Xeon and EPYC processors from Intel and AMD respectively, but also against even instances in the cloud that have GPUs in them. So these are NVIDIA A10s. And you can see here that the Ampere processors with our optimized frameworks and technology are keeping up even with GPUs in some of these cases. This is the power of the kind of box that we're delivering to you to be able to do not just video encoding and transcoding, but also value-added services like transcription. Okay, I think we'll wrap it up here. I think like maybe one more slide. I'm not sure if there is. Oh, yes. Let's go back to the. No, let's keep it on that slide because we're going to go back to the new Quadra video server, the Ampere edition. That is what we are demoing here for you today. I'm going to hand it back to Alex to kind of wrap it up for us here and maybe describe a little bit more about the Quadra server.
Yeah, as said, this server is we are very proudly to release recently, and this is one that is bring the horsepower and also the smartness into the industry, and it's available immediately right now. So it is a practical solution to everyone that can. You need the heavy lifting of the video workload and also the state-of-the-art AI solutions all in one box. Okay, thank you.
Thank you so much.